Welcome. Today's topic is adaptive resonance theory, ART. It's proposed by Carpenter and Grassman in 1987. It's one of its online clustering algorithm. It has a recurrent ANN structure, means all neurons are connected to every other neurons. It has a competitive output layer. It's used in data clustering application. It achieves stability, plasticity, dilemma. So what is this? Stability is system behavior does not change even after irrelevant events. So the system's behavior is stable. Plasticity is system adapts its behavior according to significant events. So when there are totally different events, the system adapts to that event is called plasticity. And dilemma is how to achieve stability without rigidity and plasticity. So both are irrelevant, but to achieve both, that is the work of our adaptive resonance theory, ART algorithm. It achieves the stability, plasticity, dilemma. So ongoing learning capability and preservation of learned knowledge. So the ART architecture, it has the input and output layer. This is its general architecture diagram. Top-down weights are the weights which goes from top to down, from the output top layer to the bottom layer. And the weights which goes from the bottom to top are the top-down weights. It's used to store some template. When a new input comes, it compares the new input with the already stored template. If it matches only, it can take it. So the algorithm is like we have a new pattern. It categorizes if it's nearly close to some other already available pattern that's taken as winning node. It recognizes, compares and recognizes and follows that pattern. If not, it initializes a new node and proceeds with that. ART types are ART1, it's unsupervised clustering, binary input vector. ART2, unsupervised clustering of real valued input vectors. We have ART3, ART map, fuzzy art map, dart map, and Gaussian art map. These are the types of ART algorithm, adaptive resonance theory. So this is the architecture of ART1. So we have the bottom layer, input layer, which is F1A. Middle layer is called the interface layer or F1B. And then the output layer, Y1. We have a reset module here called R. And as we can see from the input, we have connections to the reset layer, and same way from the interface layer also we have connections to the reset layer. And then from interface to output layer we have top down and bottom up weights. In the additional modules we have are the input and output layer. Other than that we have the reset module, which is this R, and then we have gain control. So the reset module, it has fixed connection weights. It implements Vigilus weight. It has excitatory connection from F1B. So this one is F1B. From there it has excitatory connection and inhibitory connection from F1A. This excitatory and inhibitory are deciding whether the weights has to be increased or decreased, whether it's going to contribute more or less to the output. The output of reset module is inhibitory to the output layer. It disables firing the output if it matches with the pattern is not close enough. So the other module we have is gain module. It has fixed connection weights. It controls the activation cycle of the input layer, excitatory connection from the input lines and inhibitory connections from the output lines. So the algorithm of ART1, step 0, it initializes the parameters L, P, initializes the weight value, and initial T, J, I equal to 1. While stopping condition is false, go for steps 2 to 13. For each training input, do steps 3 to 12. Set activation of all the F2 units to 0, the interface unit. Set activation of all output unit, and F1A unit, which is the input unit. Compute the norm and norm of S, which is sigma S1, Si. Set the input signal from F1A to F1B layer. Send the inputs from input layer to the interface layer, Xi equal to Si. For each F2 node that's not inhibited, if Yi is not equal to -1, Yj is sigma Bj Xi. Then while reset is true, go for steps 8 to 11. Find j such that Yj is greater than or equal to Yj For all nodes J, recompute the activation function, compute the norm vector, test for reset, and finally update the weights and check for the stopping criterion. We also have the recognition and comparison phases. Recognition phase, forwards transmission via the bottom up weights. Input pattern is matched to the bottom up weights and the inner product is found. Best matching node is fired. Pattern associated to the closest match is fired. If not, we go for a new flow. Comparison phase, backward transmission via top down weights. Vigilance test is conducted. If pattern is close enough to the template, it's categorized and resonance is achieved. If not, the winning neuron is reset and try for another best match. Repeat until. Vigilance threshold is, it sets the granularity of the clustering. It defines the amount of attraction of each prototype and low threshold. Adaptation, only the winner nodes are adapted. Only features common to all the member clusters are kept. So the issues, it's difficult to tune the vigilance threshold. New noise patterns tend to erode the templates. It's sensitive to the order of the presentation of data, and accuracy is sometimes it's not optimal. Example of ART1 architecture is character recognition. Thank you.